So we just derived the continuity equation. Now what we're going to do in this segment is we're going to look at a few simplifications of the continuity equation. So writing out the continuity equation in differential form. That's what it looked like. Simplifications that we can sometimes come across. First of all, we could be dealing with flow fields that are steady. So if we have a steady flow, then the partial by partial t term would be equal to 0. And what we then end up with is just del dot rho v equals 0. If we have an incompressible flow, we know for incompressible, density is equal to a constant. If density is equal to a constant, the time rate of change of density will be 0. So what we then end up with is del dot v equals 0. And del dot v, remember when we looked at the vector operators, we said that that was the divergence operator. And that's quite often whenever you talk about an incompressible flow, you always say del dot v is equal to 0. But expanding that out, what it looks like is the following. So that would be for an incompressible flow. Now, in the case of liquids for the most part in fluid mechanics we view as being incompressible. And in the cases of gases, they're incompressible for velocities less than a Mach number of 0.3. And Mach number is defined as the local flow speed divided by the speed of sound. So m is the Mach number, and a here would be speed of sound. So as long as we stay at 30% or lower than the speed of sound in air, then for the most part we can view the flow as being incompressible. And then we can simplify the continuity equation in the way that we've just seen. So the main one is whenever you're dealing with incompressible flows, you'll often hear people say del dot v is 0. And that is then just a shorthand notation for the continuity equation for an incompressible flow field. What we'll do next, we'll look at a different coordinate system for the continuity equation. We're going to look at the cylindrical coordinate system, and then we'll solve the problem. And then after that, we'll move on to momentum.